Hmm. Hello everyone, we are here to present our paper
अरे
at the
2 मिनट मेरे को स्विच करने दूंगा अभी 10 सेकंड बाद स्टार्ट कर दो.
ठीक है. Hello everyone, we are here to present our paper at the ICSES 2024 conference. The title of our work is Advancement in Disaster Prediction, a systematic review of earthquake, flood, and cyclone forecasting technique. Our team consists of Pratik Shetty, Shubham Varma, and myself, Sachin Tripathi. We would like to thank Professor Chitra Bhole for her guidance throughout this research. Next slide. So this will be the presentation overview. We'll start with the introduction, then we'll introduce the disaster prediction, then we'll discuss the importance of machine learning and deep learning in disaster forecasting. I will give the overview of earthquake prediction model, and flood prediction, then cyclone prediction, and comparative analysis of all these models, and then key challenges in disaster prediction, and then we'll conclude and give the future research directions. Next slide. So in the recent year, disaster prediction has significantly improved due to advancement in machine learning and deep learning models. Our review focuses on the technique used for predicting three major natural disasters, which are earthquake, flood, and cyclone. For earthquake prediction, we explore the spherical convolutional LSTM model, which effectively analyzes the seismic data. In flood forecasting, we discuss the hybrid CNN LSTM model, which combines the convolutional and recurrent neural network for better accuracy. For tracking cyclone, we highlight spatio-temporal fusion network, which uses data from multiple sources to improve and check the accuracy. While these advancements are promising, key challenges still exist. Issue like integrating diverse data resources, ensuring model scalability, and managing high computational costs are hurdles that need to be addressed. Next slide. So natural disasters such as earthquake, flood, and cyclone have widespread and often devastating impact on communities, infrastructure, and economies worldwide. And the ability to accurately predict this event is essential, not only to improve the preparedness, but also to reduce the overall damage and save lives. When we forecast this event effectively, response team can mobilize, communities can prepare, and resource can be allocated more efficiently, minimizing their toll on both human life and economical resources. The traditional forecasting method have provided fundamental foundation for disaster prediction, but recent advancement in machine learning and deep learning have taken these capabilities to a new level. Next slide. By integrating these cutting-edge technologies, we can analyze complex data pattern more deeply, which lead to a more accurate and reliable prediction. This prediction model not only improves the accuracy, but also allows us to respond more quickly to incoming threats, significantly enhancing the disaster preparedness. In this presentation, we will explore the latest advancement in predictive models, especially more precisely for design for earthquake, flood, and cyclone. We will examine how this model work, their unique innovation each model brings to disaster prediction, and the challenge involved in applying the large-scale model. Next slide. So in this section, we will discuss several advanced techniques for predicting earthquake, focuses on unique feature and advantages. So one significant advancement is the spherical convolutional LSTM. This model is unique because it incorporates the Earth's curvature into its prediction. So traditional model often treat the Earth as flat, which can overlook important global connection. By using spherical convolutional, this model captures the spatiotemporal correlation essential for accurate prediction. In this process, data while considering the Earth's three-dimensional structure, which enhances the prediction accuracy. Another noteworthy model is ADE-NET, designed for earthquake detection in areas with the limited data. It specializes in identifying centralized acoustic signals which can serve as early indicator of seismic activity. Next, we have the attention-based bidirectional LSTM. This model offers a sophisticated approach to extracting temporal features from seismic data. By using an attention mechanism, it prioritizes the most relevant time frames in the data, allowing it to focuses on critical signals that may indicate an upcoming earthquake. Further part will be covered by Shubham Varma.
So let's see the comparison of earthquake prediction models. First, we have the spherical convolution LSTM. This model stand out because it recognizes a crucial aspect often overlooked in traditional model, the curvature of the Earth. The most model treat the Earth as a flat, which simplifies the spatial processing but can limit the accuracy when making global prediction. By incorporating spherical convolution, this model effectively handle large-scale spatial temporal dependencies for factor in predicting seismic activity over vast region. The second is that ADNet is designed to work with the decentralized acoustic signal data is often more accessible in remote access areas. One of its core strengths is the ability to perform well even when the amount of available data is limited. By leveraging deep learning techniques specialized for acoustic signal detection, ADNet can still offer a robust earthquake prediction, even in scenarios where sensor networks are not densely established. This makes it indispensable in data scarce environment. Lastly, we have the attention by directional LSTM model that focus on short-term time-sensitive forecasting. It uses of attention mechanism allows it pinpoint critical temporal feature in seismic data, essentially focusing on most relevant data point that might indicate an impending earthquake. To summarize this, the spherical convolutional LSTM excel at a global prediction and ADNet offer a solution for data limited regions and attention based bidirectional LSTM enhance short term forecasting. Next slide. Let's see some flood prediction techniques. So moving on the flood prediction, we encounter some equally advanced techniques, particularly those that handle both spatial and temporal data effectively. One of the most prominent model is area of CNN LSTM hybrid. Uh, Convolutional neural networks are widely used for analyzing spatial data and long short-term memory LSTM networks are well suited for time series prediction in flood forecasting, where both spatial and temporal complexities are integral. This hybrid model excels by combining the spatial feature extraction with CNN and temporal forecasting strength of LSTM. This model can analyze complex patterns related to the rainfall, water flow, and environmental change. CNN LSTM hybrid is particularly adept at predicting both short-term flood events and making long-term projection about the flood risk. In addition to hybrid model, we also have ensemble learning models that is like random forest and XGBoost, which are frequently employed in flood prediction tasks. These methods combine multiple models to improve prediction accuracy by aggregating their outputs. Random forest and XGBoost may struggle with a large scale data set, particularly in regions that have extensive historical flood data. This can lead to the computational bottlenecks. For this, we have Despite this, their accuracy and adaptability make them powerful tools for localized flood prediction. Next slide. We have another model that is federated learning for collaborative flood prediction, a recent and highly promising approach for flood prediction. Federated learning in disaster scenario data from various regions or organizations are highly sensitive or proprietary, limiting the ability of these entities to share data for collaborative prediction. Federated learning is essential valuable when disaster prediction efforts spans multiple regions or distribution at it enable collaboration while maintaining data privacy. And the next model is that big data and crowdsourcing in flooding and mapping. We cannot overlook the role of big data and crowdsourcing in improving flood prediction. The sheer volume of data available today from satellite, imaginary sensor network, and even citizen report through crowdsourcing platform has transformed flood mapping. One specific method involved the use of unit segmentation technique with the Sentinel-1 satellite imagery. These techniques allow for a real-time dynamic mapping of flood-prone areas. The data generated through this method is constantly updated, giving decision makers accurate real-time insight. This is invaluable during the flood event, enabling rapid response and better coordination for evacuation, resource allocation, and disaster relief efforts. In conclusion, you can say the advancement in disaster management both for earthquake and floods are truly remarkable. The spherical colostrum, LSTM, ADNet, and attentional based bidirectional LSTM model for earthquake and the CNN and ensemble learning techniques for the flood. Over to the Pratik.
So in this slide, I'll talk about the cyclone prediction models which we have included in a review paper. So first one is spatiotemporal fusion networks. These models use both spatial and environmental data to predict cyclone movements. They handle complex time-based patterns, helping to forecast cyclone paths more accurately. Then we have deep attention networks. So these networks focus on the most important features in satellite images to better estimate the strength of cyclones. Then we have CNN models, which are used to process satellite images and track cyclone movements. These models are important for real-time cyclone monitoring and disaster preparation. Here we'll talk about some of the models which we have considered. So first we have hybrid models. So these models combine different techniques such as spatiotemporal graph neural networks to predict where cyclones will move and their potential impact. By mixing methods, the predictions become more accurate. Then we have reinforcement learning, where these models keep learning and improving as it receives new real-time data, helping to better track cyclones over time and increase prediction accuracy. Then we have transfer learning. Transfer learning takes a model trained in one region and adapts it to work in another region. This is useful when there isn't enough data in certain areas, helping to overcome data limitations. So in the right side, we can see there is a comparison of various cyclone models in terms of their accuracies. Next, we'll talk about challenges in disaster prediction. The first one is data integration. There's a lack of consistent high quality data across different regions, which makes it difficult to predict disasters accurately. Then is computational complexity. Advanced models like deep learning require a lot of computing power, making it harder to use these models in real time. Then there is model interoperability, which basically suggests that models tend to work in one area may not work as well in other regions with different environments. So this limits the model's ability to generalize. Then in terms of future direction, we can improve by better collecting data with methods like remote sensing through satellite data and crowdsourcing, which will help us to collect real-time data. We can implement lightweight models that can work in areas with limited computing resources. Then data integration we can work upon using a wide range of data and environmental non-seismic data can improve overall disaster prediction. When we come to the conclusion part, the significant advancements which involve machine learning and deep learning models have made big improvements in predicting disasters like earthquakes, floods, and cyclones, leading to better forecasting. Then these advancements in real-time capabilities enable faster, more accurate predictions, allowing for better alerts and better disaster preparedness. Then we come across challenges which includes the quality of data, how to integrate it effectively, and the large computational resources required by complex models. Then cross-disaster models that can predict multiple types of disasters by sharing common features would be more efficient and accurate. When in terms of prediction accuracies, deep learning models like CNN, LSTM hybrid, and attention-based networks have greatly increased the accuracy of predictions. Then is regional adaptation, uh, where models need to be adjusted for different regions to work well. Transfer learning can help improve prediction for areas with limited data. So this explanation simplifies the core ideas, making it easier when it comes to making presentations. So that's it from our side. Thank you for listening.